the section about elastic potential energy. And if you think back to chapter 5, where we studied about energy, we looked at the spring mass system, and we said that it can store energy when the spring is compressed or the spring is expanded. And we looked at the value of that energy. So that's the spring potential energy, same as elastic potential energy. It's half kx squared. Yeah. So the potential energy due to the spring is half kx squared, with x is the displacement. So x is not the total length, it's the displacement from equilibrium. Okay, so you always have to measure it from equilibrium. Okay, and remember we did this kind of graph where here's the force that's applied, here's the displacement, then the shaded area under the curve, which is this gray area, gives us the work done, or the energy, which is half base into height. Half base is x, height is kx in magnitude. So half kx squared it becomes, yeah? Okay. So if we consider the energy transformations in our spring mass system, we've looked at these diagrams before, and now we're going to think about them in terms of energy, okay? Total energy is what we're going to write over here. So in the total energy, we have to consider kinetic energy and potential energy. And since the system is isolated, there's no friction, then our energy has to be entirely conserved, yeah? So although the amount of kinetic and potential energies can vary, so there can be transformation between one and the other at any given position, the entirety has to be constant. Yeah. So for example, if they add up to 100 at this position, they must add up to 100 at this position, or any position. Okay. So here's our general formula for kinetic energy, 1/2 mv squared. There's no rotation here, so no rotational kinetic energy. No gravitational potential energy. It's all on level. We can define this as our zero reference for potential energy, this height. So we just need to consider the elastic potential energy, which is 1/2 kx squared. So if we start with having pulled the spring out to this maximum amplitude position, then the spring is storing some energy because we have extended it, and it's storing that 1/2 kx squared. There is no motion, our velocity is 0, therefore there's no kinetic energy. So this becomes our total energy. Yeah? Then the object moves to equilibrium through the intermediate positions, which we haven't shown. Okay, in the intermediate positions, there's a little bit of kinetic energy and a little bit of potential energy, right? And that keeps changing till we get to this equilibrium where all the energy becomes only kinetic. And that kinetic energy is 1/2 mv squared. We know that the V is maximum at equilibrium. We saw that earlier. So 1/2 mv squared, whether the V is positive or negative, doesn't matter, okay? Since you're going to square it anyway. What about the potential energy? Well, that depends on x. X is 0 here, so there's no spring potential energy. So this is my total energy here. This must equal this, yeah? Since energy cannot be created or destroyed, energy can only be transformed. So here it's transformed from potential energy to kinetic energy. And then as the spring gets compressed, it overshoots to the other side, compresses the spring. We're going to convert the kinetic back to potential energy, which is stored in this compressed spring. So once again, we have kx squared, and we have 0 kinetic energy because we are at the other extreme. The object is momentarily stopped. So there's no kinetic energy. We come back to equilibrium. We're exactly in the same position. We have exactly the same kind of energy, 1/2 mv squared. This is not correct. This needs to change to m, and I'm just going to do that for you. Okay, so the energy here is 1/2 mv max squared, not k squared. Okay. So just going to cut this out. Okay. And here we are back to this equilibrium position. So we have exactly the same. And sorry, here we're back to our starting position. So we have exactly the same energy here. We're extended by this maximum amplitude, 1/2 kx squared. Yeah? So our energy is shuttling between potential, kinetic, potential, kinetic, potential, and it keeps doing this, right? And the in-between positions, there is some kind of summation of partly potential, partly kinetic. If you're closer to this side, then you have more potential energy and less kinetic. As you come closer to here, more of that potential energy is getting converted to kinetic. Yeah? So take some time to understand this and be familiar with all the different positions, yeah, and their energies. Okay, so let's do a simple problem based on the spring mass system. We can use a toy gun spring mechanism to ask and answer two simple questions. So here's a toy gun, this is the spring that we're interested in, and this is our little projectile, our object, okay? You would have done this kind of projectile experiment in your second lab. How much energy is stored in the spring of a toy gun that has a force constant of 15 newtons per meter? That means K is 15 newtons per meter, and is compressed 0.15 meters. So here is X. This is K, this is X. 1/2 kx squared is going to give us that energy stored. Yeah? Part B. If you neglect friction and the mass of the spring, at what speed will a 2-gram projectile be ejected from the gun? So all of that kinetic energy, 1/2 kx squared, that was stored here, will be transferred to the kinetic energy of the projectile as soon as the spring is released. So you set 1/2 kx squared equals to 1/2 mv squared, where m is 2 grams. Don't forget to convert it to kilograms for the NKS units. And that should allow you to calculate your potential energy in part A as 0.56 joules, and part B, your velocity as 23.7 meters per second. So in summary, we have seen how the spring mass system has a variation of position with time or displacement with time, right? And this is a cosine curve. And then how it's related to the velocity time curve, which is a sine curve, and then the acceleration time curve, which is another cosine curve with a negative sign.